Before we get into the subtraction algorithms for integers, I just want to remind you of what you've been reading in Principles to Actions. The 8 math teaching practices. Now, this is different than the standards for mathematical practices that I had in Module 7. This is the math teaching practices, establishing mathematical goals, promoting reasoning and problem solving, mathematical representations, meaningful mathematical discourse. Now, here's the two I want you to focus on as we go forward. Pose purposeful questions. And then, of course, we've already seen building procedural fluency from conceptual understanding, support productive struggle in learning mathematics, productive struggle, let it happen. And then finally, elicit and use evidence of student thinking. As we go through this module, you've seen it in module 6 as well. We want students to engage in the thinking. So you have to elicit student thinking. And then as they do, and as a student, 2 students, 3 students come up with ideas and share them with the class, and you critique the reasoning of others, then we use that student thinking as the final straw there, the final rule, the final algorithm. But let that emerge from student thinking. So elicit and use evidence of student thinking. Why? Because we have a problem. I'd like to resource this. This is not anything you'll be reading. I'm just going to share with you a good book about education called Empowered Educators. And in it, they say this. University of Oxford researchers estimated that 47% of more than 700 present-day occupations are susceptible to being computerized. As I sit here in May of 2023, AI, ChatGPT, the conversation on AI is probably making this even greater than when this book was written. Many of the fastest growing and highest paying jobs did not exist 10 years ago. Mobile applications, digital strategists, market research data miners, social media, sustainability, jobs that didn't exist. So the point here is we don't need to train our students to be computers and be able to compute things well in mathematics. We need to teach them to think. Students entering school today will leave to work in jobs that do not yet exist. Think about that. As an elementary educator, you're going to be teaching students that one day in 10, 15 years will leave your classroom and enter a job market and work in jobs that do not even exist. They'll be using knowledge that has not yet been discovered, technologies that have not yet been invented. They'll be facing complex problems our generation has been able to solve. As a consequence, the top skills demanded by employers are not merely following directions and counting change, but the ability to make sense out of complex information events, think creatively, solve novel problems, work well with others, engage effectively in cross-cultural contexts, and manage many forms of media, as well as quantitative data. So as we engage in this, we're going to be teaching an old-fashioned lesson about integers, but in a new way, I hope for you, in that we're not going to focus just on getting the answer. Not just on getting the answer. We're going to focus on the thinking that leads to getting the answer. In order to enable very diverse students to learn the higher order skills once reserved for the tiny few, teachers need a range of new skills. They must understand content more deeply and flexibly. Pause there for a minute. That's why you're in this class, is to understand mathematical content more deeply and flexibly. Teachers must understand the science of learning, how children learn. As I've been taking you through this, and especially if you think back to using concrete manipulatives, base 10 blocks, integer chips, moving towards more like drawings and figures, transitioning to ultimately abstract. So we have images in our head of number lines, of chips, of blocks, and we can imagine how things work. We have to, as teachers, understand the science of learning. Across many subject areas, we're focusing on math, of course, but as elementary teachers, you have to be able to do this in lots of subject areas. You must understand how to support language acquisition for the use of native and non-native students. You must develop teaching strategies that foster analysis and reasoning. You must continually incorporate appropriate technologies into your teaching practice. Whoa. Chalk and talk methods used to impart facts will need to give way to methods for engaging students in applied learning. Chalk and talk would be like what I'm doing right now, online class. If you're in my classroom, it would not be like this. We would be engaged, you'd be active, you'd be standing at the whiteboards, you'd be working. But I want you to be aware as a future teacher, you have to get your students engaged in applied learning. Teachers will be increasingly called on to collect and analyze a range of assessment data to ensure all students are learning, provide differentiated teaching to students of varying abilities in the same classroom. In this class, what I hope you're learning is the different ways that you can meet the needs of students. Some students are going to have to stay in that concrete manipulative world longer. Some students will advance to the abstract symbolic, written symbolic world faster. And you have to be ready to challenge the ones that need to be challenged and support the ones that need to be supported. All of these expectations have implications for how teachers are trained, the supports that they receive early in their careers, and their ongoing professional learning. You're at the beginning of this by taking this class. I hope that I'm giving you the things that you need to prepare you for the future. But let's get into it. The meaning of subtraction. First of all, we are going to start, as I said in the slides, we're going to start by thinking of subtraction as takeaway, fully acknowledging that there's takeaway and comparison, but we're going to focus on takeaway. And in our standards, we see things like this. Look at this. Understand addition is putting together and adding to, and understand subtraction is taking apart or taking from. This is a kindergarten standard that we start our kids thinking about addition and subtraction. Grade 1, use addition and subtraction within 20 to solve word problems. Adding to, taking from, putting together, taking apart, and comparing. Did you see that? Subtraction as taking apart, taking away, and comparing. Interesting. Grade 2, use addition and subtraction within 100. Taking from, taking apart, comparing. We have to teach our students how to think and recognize when addition and when subtraction by grade 2 should be used in what situations. Explain why strategies work. Now that takes us back to previous modules when we were subtracting. I shared with you lots of strategies there, and we will explain why they work. It's part of fluency. Grade 4, understand addition and subtraction of fractions. And we're going to get to that later in this course, but again, joining and separating parts. Grade 7, apply and extend previous understandings of operations with fractions to add, subtract, multiply, and divide rational numbers. Apply and extend previous understandings. See, the standards are written in such a way that you learn things back in grade K that you leverage. So by grade 7, you're still thinking about subtraction, let's just say for now, the way you were thinking about it earlier on. And we're going to use those ways of thinking with rational numbers. Rational numbers includes the integers. And as I mentioned in the previous module, we're going to get to this now. Understand, not mimic, not memorize, but understand subtraction of rational numbers, integers, as adding the additive inverse. That is, p minus q is the same as p plus negative q. I tried to drop that hint in the previous module about how addition can feel like subtraction. And this module, you're going to see how subtraction feels like addition with integers, and you'll see that. And we'll see that both with chips and with a number line and with real world context. Now, I've been in this game for a long time, and I have seen and heard high school teachers particularly are bad about this. They'll say, what if I told you there's no such thing as subtraction? Or they'll say, I don't believe in subtraction. They'll say to students that subtraction does not exist. Now, first of all, subtraction has existed in kindergarten, first, second, third, fourth, fifth, sixth, seventh, eighth grade. Why is it that when they get to high school, somebody tells them that subtraction doesn't exist? It's insane. But look, subtraction is taking apart, taking from. Subtraction, taking from, taking apart, comparing. Subtraction, taking from, taking apart, comparing. Subtraction strategies. Grade 4, separating parts. Grade 7, subtract. Understand subtraction. Of course subtraction exists. We should continue to leverage. And we're going to focus on a grade 7 standard. Understand subtraction. Now, if you're saying to yourself, I'm never going to teach grade 7, fine. But you need to know, if you teach K1, 2, 3, 4, 5, or 6, you need to know how you are setting the stage. That's why I'm showing you all these standards. You're setting the stage for success in grade 7. So be aware of the role that you play in the lives of the student. How do we get students to understand subtraction as adding, additive, inverse? All right, so we're going to use our chips again. Yellow is going to be positive, red's going to be negative. And if you had to use the manipulatives to model 5 minus 3, and let's focus on subtraction as takeaway. Here's what it literally means. The first number tells you how many you start with. Subtraction means takeaway. And the second number tells you how many you should take away. So you're going to take away 1, you're going to take away 2, and you're going to take away 3. And what's left, of course, is 2. Now, you should go to the little online virtual manipulative tool, pause this video, and engage in this subtraction problem just as I did. You'll see you need to go through it so you can feel the trajectory of learning. Pause and go play. So 5 minus 3, the way it would look is you'd start with 5 chips and then think about subtraction. And this is why it's so important that whether you're teaching K or 5 or 6, whatever grade level you think you'll be teaching in the future, you're setting the stage because subtraction means takeaway. And so if there are 5 chips and you take away 3, boom, 2 remain. Now, we're just starting the process. Please engage so that you can feel it and work your way through, maybe with some productive struggle, to the next one. So of course 5 minus 3 is 2, but now what about this? What about negative 5 minus negative 3? And before you even start, I just want to remind you, in the previous module, you saw the video of my son Zachary, and he had a song he might have to sing at this stage. Let's see, how do I do this? I can't remember. Let me sing the song, because the goal is just to get the right answer, not the thinking behind it. Or sometimes teachers teach these little strategies like, oh, there's no such thing as subtraction, so change the subtraction to addition, and then you change the sign over here. This is what you do. You go chop, chop. Chop that into a plus and chop that into a plus. That's not mathematical. That's just a way to remember how to get the right answer. Hey, what I would say, if all we care about is the students getting the right answer, then have them grab their phone and just say, what's negative 5 minus negative 3? I hope you can see it, but it's negative 2. If that's all we care about is the right answer, then you could just ask Siri. And that's just as mathematically thinking as going chop, chop. So instead, let's actually think. Now, 5 negatives, 5 red chips. Now, what does subtraction mean? Take away. What am I going to take away? 3 red chips. 1, 2, 3. What remains? 2 red chips. See, you don't need any rules. You don't need chop, chop. You don't need some song or rhyme or whatever. All you need is to think. You start with a quantity, 5 reds. Subtraction means take away. And the next number tells you what to take away. Now, cognitively speaking, 5 minus 3 and negative 5 minus negative 3 are the same. The only difference is, are we talking about yellow chips or are we talking about red chips? Other than that, it's the same story. Hey, pause the video, go to the virtual manipulatives, play with this for a moment, please. Do you see how thinking can play a role here? We don't have to look at a math problem like negative 5 minus negative 3 and go, oh, wait, what was the rule? Is it chop, chop? Was it crisscross applesauce? Was it same sign, add and keep? Like what of all the things that you learned, all the rhymes, poems, songs, tricks, what trick would you do now? You don't need any tricks. Just follow what you understand to be subtraction. Negative 5, subtract means take away. Take away 3, what are you left with? 2 negatives. That's all you got to do is think about what subtraction means. All right, great. Now, with those two, it's, like I said, cognitively equivalent. Either you're starting with yellow chips and subtracting some yellow chips, or you're starting with red chips and subtracting some red chips. But what happens when you have something like, oh, wait a minute. Forgot about this. I wanted to get to the hint about the additive inverse idea. An additive inverse idea is this. How come the additive inverse works? How come chop chop works? Well, this is where you can start planting a seed like we did back with addition. -5 minus -3 is equivalent to -5 plus 3 because why? If you introduce some zeros, 3 zero pairs, by introducing 3 yellow chips, you've created 3 zeros. And when you create 3 zeros, you can remove those zeros, thus the subtraction, leaving you with the -2. And so, as you saw in the previous module, -5 plus 3 and -5 minus -3 are equivalent because of the way the math works here. It's about the structure and the reasoning. I hope you see it. We're going to see it in the next one as well. But yeah, like I said, what if you have to subtract something that isn't there? How do you manage that? So in this case, you've got 5 positives, 5 yellow chips, and then you're supposed to subtract, and you're supposed to subtract red chips. How do you subtract red chips when no red chips exist? Well, you productively struggle. Now, I would encourage you to pause the video right now and think about, like, reflect back on the last module. Even reflect back on this. Is there a way that you could think of to make this visually work? 5, take away -3. 5 yellows, take away 3 reds. Pause the video, think for a few minutes. Well, here's how it could work. Now, you learned previously in the last module that if I do that, I still have 5 positives and I've just added a 0 pair. And I made the analogy of young children would say there's 1, 2, 3, 4, 5, 6, 7. There's 7 monies because they don't know about value. But these 7 monies, so to speak, have a value of 5 plus 0 is still 5. What you have represented here is 5. Just like 3 coins, a quarter, nickel, and a dime, don't represent just 3 coins, they represent 40 cents. This collection of chips represents 5. 5 plus 0. As does this collection of chips. I still have 5 plus 0 plus 0. As does this collection of chips. 5 plus 0 plus 0 plus 0. That is, as long as I introduce 0 pairs, I still have a collection of chips that has a value of 5. But now look at this. It says start with 5. Okay, I have 5. Remove, subtract. What should I subtract? 3 negatives. Subtract them. Subtract 1. Oops. Subtract 1. Subtract 2. Subtract 3. And if you removed those red chips, what would you have left? 5 yellow chips. You'd have 8 chips. Hey, you got to pause on this one. Pause the video, go to the virtual manipulative tool, and try it for yourself. So the problem was 5 minus -3. So 5 yellows, 5 positives, and then you're supposed to subtract 3 negatives. You're supposed to subtract 3 reds. How do you subtract 3 reds when there aren't any reds? There's the conceptual challenge that we face. And to overcome that challenge, we introduced the idea of the 0 pair. So if you bring in a 0 pair, this collection of chips still has a value of 5. 1, 2, 3, 4, 5 plus 0. Plus another 0, plus another 0. I got it. Yeah, I did. So I have these 0 pairs. Let me just throw them over here. So 5 plus 0 is still 5. But now I can do what the problem stated. I can start with 5, which I have here representationally, and I can subtract 1, I can subtract 2, I can subtract 3. And when you subtract 3 red chips, you're left with 8 yellow chips. Now, this is an important moment, is for us to see how that worked. Let me put those back for just a minute. Now watch how the addition idea makes sense. I started with 5. Did you see what I did? I added 3 0 pairs. And when I subtract, when I remove the red ones, then what's left is equivalent to 5 plus 3 because I brought in the 0 pairs, and then when I subtracted, I'm really left with 5 plus 3. So -5 minus -3 is equivalent to, just look at it, 5 plus 3. That's the understanding we want our students to have, the flexibility, the fluency to make sense of that. So yeah, when you do this, when you add in those 0 pairs and then you do subtract, it's equivalent to adding 3's. 5 plus +3 and 5 minus -3 are equivalent in terms of the action. And I love thinking about this operation as action because it is. You're either removing, there's the action, or you're combining, there's the action. But in this case, you can see it, that they're equivalent. All right, try one more. -5 minus 3. -5, so 5 reds, minus, take away, 3 yellows. How do you remove 3 yellows when all you have is 5 reds? Will you give it a shot, please? You can go to your virtual manipulatives and try it and then come back and see what I have. Did you give it a go? We had 5 negatives. And from the 5 negatives, we were supposed to subtract 3 positives. Well, there's no positives to subtract, so we bring in some 0 pairs. And remember, I'm supposed to subtract 3 positives, so I just need 3, I just need 3 0 pairs. So in terms of value, I've got -5 plus 0 plus 0 plus 0. I've got -5. And from that collection of -5, I'm supposed to subtract 3 positives. There it is, -8. It is -8. And as soon as I subtract that, now you can see it, I hope. It's the same thing as having -5 plus -3. It's the same thing as combining -5 and -3. It's an important connection to make visually that you can see removing the positives has the ultimate effect of adding those 3 negatives. There you go, -5 minus 3. If you have -5, which is really what I have here in terms of value, and I remove 3, 1, 2, 3, I would have the -5 and the -3, which is -8. And boy, that sure does look like a -5 plus -3 now. So we're seeing that additive inverse. We're understanding it visually. At least that's the goal. Now, I'm just taking you through 4 examples here. You know that with kids, this is going to take time and sharing and discussion and navigating that whole productive struggle until kids start to see it. And I wouldn't even tell them this. I would wait for a kid to say when they're done and go, look at this. This looks like -5 plus -3. It looks like the same thing. You say, yes. And as soon as a kid or many kids share it, you have them share it with the class, they make a viable argument, you critique the reasoning of others, and once it's settled, here's the phrase we use in the psychology of math education. We say, once it's taken as shared. So the class as a whole, you get this sense that the class as a whole has said, yes, that's true. -5 minus 3 is the same thing as -5 plus -3. It's taken as shared. Now it can become a rule as it emerges from the thinking of the students.